Hi, in November 2024, Blackberry released QNX DP8. It's free of charge for non-commercial project. So I decided to make a brief tutorial that will explain the basics of the QNX. Tutorial is based on some practical exercise and it's divided in a few parts. In the first part, we will set up QNX environment Qemu. Then we will write some simple resource manager so you can get familiar with the basic QNX utilities and IPC mechanisms. Next, we will take a deeper dive into the QNX internals with Tracelogger utility. And as the last part, we will make our resource manager secure with the help of Secpols. The installation process of QNX software development platform is shown in detail on Blackberry page, so I will skip these steps. Here are the videos that will guide you through this. Source code and important links are available in the video description. If you like this topic or you would like to know something more about some other QNX topic, let me know in the comments. Okay, so what we will be trying to do is to set up a Qemu and run on top of it the QNX operating system. So what I'm running right now is a Windows 10 machine with virtualization enabled. You can check the virtualization status in the task manager. And what we need to do step by step is to first install the Qemu. You can grab it from this web page. I just downloaded the latest version. So let us try to install it. We'll install all the features. Okay, installation took a while, but it was successful. Now we should be able to run the QEMU. Here I have a QEMU path script that should start QEMU instance. Probably will not have a network correctly set up. I'll go to command line and try to start it up. Okay, QEMU is not, this command is not visible. This is because we need to add the Qemu to environmental path. So let's add the path for Qemu here. It's the default one. Let's try to start again the Qemu instance. Yeah, okay, now it's better. Now we were able to start it. Let's check the... Yeah, it booted up with some default architecture and default VM. Okay, looks good. Now we can try to use our Qemu to run some QNX instance on top of it. I will just create a new workspace in our QNX Momentics toolsuit. And let's just create an empty project. We'll run x86 architecture. We need to create a new launch target. QNX virtual machine. Next. We'll use this architecture. We can set these options as default. This is because anyway, this command that is used to start up the Qemu will not work on Windows, and we will use our custom one. Okay, let's click finish. Now what we are seeing here is Momentics IDE is creating for us all the simple and basic image of the QNX. So creating the IFS file system and also all the some data partition and some setup scripts that we'll be later on able to edit and see here. This is the image that we will be using to boot our system, the ifs.bin. Okay, let's try to use this image. We'll go to this place and just put our boot script here. Let's see, what is the path for our image? Here we specify the kernel file, ifs.bin. So this one will be used. Also as a drive, this Qemu will be used, and this is this one. This will be our data storage. Okay, we failed. And this is because we are missing a virtual network interface. This we will install in a second. We could run this without it, but just by removing this part from the script. If we would do so, then we will not able to SSH into our QNX image. And we want to be able to do it, so let's just install the second utility that we need. So we need virtual network interface. You can choose multiple ones. I will be using this OpenVPN. I already downloaded the binary, so let's just install it. Take this tab utilities. Okay. Well, let's just check if new interface was created. Config. Yeah, I think this one is the new one. Your name will be a little bit different and something like local area connection. Okay. Let's try it out. Because of the special characters, I see we run into some problems in the string. So I had to go to network connections, and you can see here in the network connections that I have right now 2 tab adapters. I added new one, the utility that I installed, add new tab, virtual interface adapter, and I just renamed it to Qemu tab. So we know which one is this. And here in this Qemu script, I've changed also the interface name, so they are now matching. Yeah, and if I go to command line, now we have unknown adapter Qemu tab. Okay, and yeah, let's start it. You can see that startup is happening, booting from ROM. Those logs are from our startup scripts mounting file systems. Let's check in the QNX IDE where we can find the code that is doing this. So here, if you do any addition here, the startup scripts will change. What we can try to do next is to start our example application on this VM. Okay, so we also need to set for our tab interface the IP address, the fixed one, because there is no DHCP server running on our PC. And then you can try to SSH manually from PowerShell, from any other command line. I had to add this one, otherwise I had some problems with authentication. The default password for root is root. And now we are inside the QNX. So from the QNX Momentics, we can add a new virtual target connection. So we will be able to run our test app directly from here. to do it, new launch target, QNX target. We put the IP address from the machine. The port is the one that is used by QCon. This is a tool used for connecting all the debug interfaces towards the Momentics IDE. So now it's good, and now we see we will be running a test app on this target. So let's try to run it. We see that the execution was successful. If we go here to run configurations, we can select our configuration that is used to start our application on the VM, and here in upload, remove this checkbox, and this will prevent from removing the binary from our target, so it will be visible also here in the console /temp. We have our test app, and we can just start it manually. Okay, so now that we have our Qemu and QNX system working, let's make some small project. An application that will act as a fault manager. Imagine a situation in which there are multiple applications, some can crash and or have some errors, and in this case we want to have like one database that will store all the faults that all the applications had. The fault request shall contain just a simple fault number, and the fault manager shall offer a POSIX API read to check if it is working properly, and it shall start the faults in persistent folder. So for this we'll be using a resource manager architecture. What is the resource manager? It is a process that other processes can use it to access the hardware or just to send some messages. So all the files here, basically in the Linux realm, all the device drivers, everything that is communicating with the device and is part of the kernel can be treated in similar way. Here the difference is that all the resource managers in QNX are outside of the kernel, and they are just simple processes. So we just write another application with some special calls, and it starts to be a resource manager. There are some examples here in QNX documentation. So I took the code of one of the examples, basically start writing something. So let's go through what is here inside the code. So we have our main function, and here the main thing that is creating a resource manager is this resource manager attach. It needs a EPP, this is a dispatch handle, and the dispatch handle is quite well explained in the picture here. You have all the various forms of IPC mechanisms and the POSIX calls. There is a dispatcher that basically selects which function to call. This is the responsibility of the DPP. So if you take a look here we just assign functions and handlers for open, write, read, and so on. So all the POSIX needed APIs are here delivered. We'll be using only the IO read, IO write. There is much more than open. There is also like link, unlink, and so on. And if we don't need it, basically they will be by default assigned to some default handlers. So we do not need to care and fill all the POSIX needed APIs. Our application will be under dev fault manager. We also plan to add a pulse handler. We'll be doing it using pulse attach function, and here is our function for handling the pulses. Pulses are a way of sending small chunks of data to different processes. Normally in standard POSIX operating system there are messages, shared memory, queues, and so on. pulses are a little bit special. We don't want to block the client application waiting for the response from the fault manager. Yeah, but this is not a critical functionality, let's say, for our system. What next? We need to pass. Here we specify what are the attributes of our resource manager. So basically everyone can execute. This is just a POSIX attribute of a file. And here is the function that basically blocks the execution of the resource manager until there is a message received on the channel. As you can see, this is a single threaded resource manager. So the basic example, normally it looks like this. You have a thread pool, and you have a multiple control blocks that can handle multiple IPC requests in parallel. So every client can be handled as fast as possible. But in our case, we don't have a thread pool. We just wait in one thread, and if there is IPC received, we just call off any of those functions. So in our case, this is read, write, and pulse handler. Okay, let's scroll up and see the logic of the application. So this is our read function. What it sends the fault manager status as a string. So it returns a fixed string. Fault manager works okay right now. As you can see, the code is quite complicated. This is because here in the IORead, we cannot assume that color of this API will be able to read all the data. So that's why we need to see if it can handle all this data and so on. So there is a lot of checks here. Also, let's take a look at the write function. So basically the write function here, if we call it, then it will store new fault in the file. Here we are just taking from our buffer the past string that represents a fault number, and we just call the log fault function that will open a data log file, and it will try to write the fault number with the local time string. For the pulse handling, we assigned number 15. And if this code is received, then we just log the fault with the value that is stored in the rest of the pulse structure. And the application was started. Let's try to SSH and just check it out. Okay, so now under dev, we should see our fault manager. Yeah, let's see if we can just make a cut on it. Okay, fault manager works okay. So our read function is working. Now let's try to echo some fault to it. Now it should create a fault inside our database folder. So let's check if the file exists. So data fault log. Here we have our fault. Let's try it again. Might be one before, and another fault is created. So as you can see, it kind of works. I mean, the POSIX API is working properly. We can also use the file write, file open, file close with the from some C application. Now maybe I will tell a little bit more about the logs. As you can see here in the console, in the debug console, I also see some logs for the applications, but normally you will not have it. Then it is wise to use some kind of logging mechanism that QNX provides, and this is the slog2info utility. You use it like this, that you register an slog2info buffer, and you specify the name of the application that is using it. You can have multiple buffers for one application, and then you just use functions that are provided by QNX to log. So now the question is how to read the logs. You can just type as log to info. It will print all the logs in the system. So let's grab it by the name of the buffer. Now we can see all the logs from our folder manager. As log to info offers much more than this. So for each utility in the QNX, you can just check the usage with use or with the documentation on the web page. So what next? We also would like to test our Pulse API. So to test it, we will need an additional application. So I modified also our test app. So it will send a pulse. Basically, to send a pulse, you use message send pulse function, and you need an ID of the channel. So normally this is obtained from the path, because we know that our file manager is under this path. So we just call open and we get the ID of the channel. And this can be used for both opening a file and using the POSIX API calls and for sending the pulses. So this path handling is done in QNX using Prokenio. This is the part of the kernel that is basically responsible for handling this and communicating these IDs between the processes. Okay, so let's also deploy this application. Yeah, so we have folder manager and the test. Let's check it in. Folder manager is running, and as you can see, it is blocked on receiving on the channel 1. Okay, let's run the test. Let's see what happened. Okay, test printed hello world. So we were able to open folder manager, and most likely the pulse was sent. Let's check the slog to info. Pulse received, code 15, fold 80. Yeah, and we should also have our new fold here. It is run twice because we run it from here and then we run it manually from the terminal. That's why we have two folds. So both of our applications are now working, but the problem is that if we reboot our Qemu, our resource manager will disappear, because this is not a part of BSP. It was just copied by QNX Momentics with SCP or with QCon. So we need to bake our application into BSP. The process for doing this is quite extensively described in the QNX documentation for building the BSP. So there is a guide here. But the basic steps are the following. So we need a binary that we want to deploy. So this will be our fold manager. And we will put this binary to the BSP. Basically, this should be done by our build system. So we always, when we are building a new BSP, we'll get also all the binaries included in the BSP compiled. So we have the latest version. But for the sake of this tutorial, we'll just do it manually. So I've put this folder manager inside this VM, and what we also need to do is to include this file into our build scripts. Here there is system.build file. Those .build files are basically specifying all the parts of our image. So if you go through here, all the libraries that are inside our image are specified here. All the directories, all the contents of the files like SSH configuration and so on, everything here is described, and then it is baked into one image on the host, yeah, and then we are booting this image. So here I added the line that is basically saying this, that we will take the file from output build folder manager, so this is this file, and we'll put it under the xbin folder manager with the permissions of 555, so everyone can read and execute. The second thing that we can do is to add the startup of this. Yeah, so here is the startup.sh file. If you look for this file, it is executed, so it's some build file. So at the end of the file, I added also that the folder manager will be started, so we don't need to manually start it. So let's take a look. Here, can I just reset it? Maybe I can. No. So I'll just terminate this VM and I will start it once again. Okay, and during the startup, you can see here starting file manager is present, and also there is this start log from our folder manager. So pidgin, here you can see that now we are starting our folder manager from system xbin folder manager. So now this is a part of our system. So what we can do next is to try to play a little bit more with the folder manager and check how the signals are sent under the hood with the interaction with our test app. So to do it, we will use a Tracelogger utility that basically is getting all the logs from our system, and it is saving it to a file, and then we can analyze this file in QNX Momentics. So first I will just slide the folder manager up. So we will start a new instance. Okay, also if you take a look in dev, there is no more folder manager path here. So yeah, it is that. And now what we'll do is we will start deploy this test. Okay, folder manager can be opened, this is okay. But the test file is in the temp, and let's try this command. What does it do? First, maybe let's check what Tracelogger is doing. We'll be using -s, and it specifies for how long the Tracelogger will run. And the file that is created will be stored in dev shared memory trace buffer.qemu. This will be the file with all the traces. And what we also have in our command, let's just take a look. Okay, maybe I will just use SSH, not this. Let's paste the command. Will this work? Yeah, okay. So it's already started, but anyhow, let's analyze the command. What we are doing is we are starting the Tracelogger, starting our folder manager. Here, this wait for will wait until this path appears. So this means that the folder manager started properly, and then it will just start the temp, the test app from temp. And this is what we have inside our Tracelogger. Yeah. So how to get this Qemu file now? So what we could do is to use SCP, but also we can use the Momentics IDE. There is a QNX system information, and here there is a lot of stuff about our system present. Yeah, all the processes that we have. You can see the folder manager also, and the details of this process, like number, parameters, and so on, everything that you can get with pidgin and much more. But also what you can do is to just explore the target file system, and yeah, just put and get the files from the target. So let's just see if under dev shared memory there should be Tracelogger file here present. Yeah, trace buffer. Here it is, the KV file. I'll just copy it, just put it in the folder manager. Yeah, I did previously, so I'll override it. Okay, now let's just open it up. We'll stop this, go to the standard view, and just open the trace buffer. To load all the stuff. Here there's multiple things to see, but what we are interested in right now is this graph, the timeline graph. So let us just select our two processes that we are interested in, because here you can see a list of all the processes. Here those stripes are showing all the communication from this process that happened, and a lot of data exchange and so on. Most not relevant for our use case, so let's just select fault manager and our test app. So here we also select the trace event log. Here I enabled only the filtering of the events from the selected processes. Let's just zoom it in and see what we have here. Zoom in. Okay, here the colors are showing the states of the process that we are in. So if we hover here, we see that the test thread 1 here was blocked. And I told you previously that the process should be not blocking. So let's see on what it get blocked. So when I selecting this, it selects also on the bottom here all the events in between, and let's just see what is happening here. So we see our test thread sends a message, and this is a pulse, and this triggers the fault manager into the ready state. Yeah, the pulse number is 0F, so this is our fault. Okay, great. So next we see that this guy goes into ready, and we see it is also here in the green color. So it starts operating also and trying to access the file and so on, and this is what we see here. But the thread, our test application, is not waiting for the response, so it is blocked on something else. Yeah, and you can see that it is blocked on the close of the channel, and this is because our fault manager is single threaded, so it cannot, it's doing right now the write operations to the file, and then it will handle this close. So that's why we are blocked here. So we could optimize it by creating a thread pool and so on. Probably this would solve the problem. Yeah, but this is the way that you can see and debug what is the interprocess communication, yeah, here in this trace buffer. So that was my intention to show you this. So now I would like to tell you something more about the QNX security features. There are multiple features related to security, secure policies. If you will be writing an application or writing some driver in BSP or just configuring the system, you will probably use it in your production QNX. Secure policies are somehow similar to AppArmor Linux approach to making the operating system secure. They are mandatory access control type of security. So you have set of rules, called abilities, that control every resource of the system. Taking our example, this tackles a problem in which we only want that selected applications will be able to connect to the channel and trigger a fault in our fault manager. So without the mandatory access control type of security, it will not be possible. And with the Secpols, we'll be able to configure the secure policy in such a way that only the selected types will be able to access our fault manager. Okay, so let's take a look how in QNX these secure policies are working. There is a utility called Secpol compile that needs a secpol rule.txt file. File combines all the abilities and all the security types in the system. If we take a look, there are multiple types defined. Each application has its own type, and each type has a set of abilities. So the things that this application can do. Here, for example, the console can do a lot. It can spawn, make a forks, and make some channel connections and so on. Each ability is explained on QNX webpage. And as you can see, this file is quite big, even for our very small system. So I didn't write it from the scratch. There is this Secpol generate utility that is used to support us. From the Secpol compile and this file, this Secpol rules file, we get a Secpol binary that we then move into the image, and then this Secpol binary is used by Secpol push utility that enforce the security rules on the QNX operating system. So then the kernel controls who can access what. And as I said previously, to ease the writing of the Secpol rules, we have the Secpol generate helper utility that in production image it will not be there, but in development it is used. This Secpol generate also gets this Secpol bin, and it also gets some configuration file that is telling what types are restricted or what are unrestricted. And the Secpol generate gives us some new device, some new resource manager that lists all the forbidden abilities that the Secpol type has, and it is not like breaking the system, but it's just informing that this application should have this ability and it doesn't have it, but anyway I will let it pass. Depending on the config file configuration, you can do so. So we will see how this works in practice in a moment. So let's go back to our VM. First, we could manually deploy all the binaries and execute them, but this would be time consuming. So there is an option in mkqnx image utility that is used to generate the IFS image, to use it to specify the Secpol parameter. So we can use it in open, and this will generate as an image that will have some presets and all the utilities that are needed deployed. So let's give a try. Here I will edit our VM. Be aware that any changes that you did in the build will disappear if we rebuild it here. So just make sure that you have all your changes to the build files saved if you need them. So first we will just add a Secpol open. And we'll see what will happen. So now the image is regenerated. And we see that in output build, Secpol gen starts sh was added. So let's go there and take a look. This script, what it does. So as you can see, it is starting the Secpol generate. with the policy that is stored in data var. So this is in our read-write partition. Normally it should be stored in read-only, but for debug purposes it is done like this. We have also our config file that is telling what secure policies are restricted, what are not. And we also have our Secpol push. Loading secured policies. So first the script is called that we looked just before, and then the Secpol push is executed. So the secure policies are enforced. Try to start our QNX image once more. We'll see what changed. So now we see on the console some errors. For Secpol generate, failed to access def something. Let's ignore them for now. They are related to IOSOC, so the network driver. And let's take a look at the files under the data for the Secpol. Secpol config. Let's take a look first at the config. Config has a few lines. It says that all the secure policies are in unrestricted, with exception of denied read exec. This is the name of ability, and if any application needs this ability, probably it is misconfigured in terms of POSIX permissions. So it doesn't belong to a group that it is not owner of some file that it is trying to access. That's why we need this ability, because with this ability the POSIX permissions are no longer making any effect. So that's why this is configured by default to be denied anyway. So let's also check how our startup was changed. Previously, if you take a look at your startup sh, all the drivers and the binaries were started like this, and now we have additional part before each of the binary that we start. This is because we need to assign a proper secure policy type, and this is done by on utility. So -t specifies, -T specifies the secure policy type, and then we have for each of our application we have a specified and unique user. This is a good practice for security reasons also, but it is not mandatory to have it like this to have the secure policies work. So now let's try to deploy our resource manager and our test app, and we'll see what will happen. So now fault manager started, our test application, hello world, okay. Let's see the logs, what happened. There's nothing special here happening. Okay. We have a Secpol generate error. And what it is saying that the fault manager type qcon t failed to access data fault. And previously I told you that we are running on unrestricted, but anyhow we Secpol generate, and this Secpol generate because of exactly the reason that I told you, that we have this line. If you take a look at data directory, the owner is root, and only the owner have write permissions. And here, if we go to bit in, here we see that our user ID for fault manager is 29. Yeah, this is the same as here, and this is not root. Yeah, so it can't access. It can't access, and also like any type of this failure is a restricted one. Yeah, as we saw in the config file. To see on what Secpol type is used by by any application, we can use also pidgin. There's a command in QNX documentation for pidgin. It tells us what kind of type it is using. We did not specify the type, but it was done automatically by the Momentics IDE because we clicked here and then it was deployed and started using probably on with this and with the user 29. So let's slay our fold manager and start manually as we expect to be started on the system. We plan to have our dedicated type for fold manager. The name will be fold manager underscore t, as this is the standard naming convention for the secure policies. So we will start it like this. We'll not start it with a unique user. Okay, no such file, that's fine, because we need to specify the full path. Okay, it was started. Okay, it will not, it will start in foreground, so let's add -d. Okay, and now let's take a look. Now we have correct security type, and the user probably will be root or the console user. Okay, it is root. There are zeros everywhere, but this is fine. We can try to start also our test app with the on. Okay, hello world. I think it works properly. We also started as root, so we should have also the file in data. Yep. And we have the error code. We did some experiments with secure policies, but they are not a part of the system. To make them part of the system, we need to create file that I mentioned, this one. To get the contents of this file, we can use the def secpol generate, yeah, from the secpol generate utility. So let's take a look at this file. Def secpol generate. First, maybe any errors. You can see here only the errors, so everything that was blocked and affected how the application ran is here. So, for example, our first attempt to start the fold manager with the qcon failed to create data log fold log, and it was reported here. Yeah, so the fold manager misbehaved in this scenario. And now let's also take a look at the generate policy file, and this file listed all the missing secure policies that should be in place, but they were passed by the kernel because the types are unrestricted for those. So if we would run a restricted system, each of this would be a fail, yeah? So our system probably would not even boot. So what we need to do is to just take this file and put it in our system here, and then use the Secpol compile. It will compile into binary, and then we should not need any more change it for this use case. So as you can imagine, generating of this file is really difficult because you need to have like all the use cases, all the possible allowed use cases compiled here. Okay, let's do it. So we will just grab this file using QNX system information. We'll go here and def secpol generate, and it will be policy. This we will copy to our secpol file. Okay, let's take a look if there should be also our test app. Yeah, and as you can see, our test app has the channel connect to fold manager.t, and this lets the application to send an event to this type. So we should be okay if we restrict this one. You can also take a look at the other abilities, what they do. So here there is like description, overall description of the abilities, what they do, what they mean, and how to interpret them. For our experiments, we'll also change the config file of the Secpol, so our secure policy for the test application will be restricted. Will not restrict whole system. So data Secpol config, and here we will add type restricted. Okay, permission denied. We cannot access this file, so let's change the owner. As you can see, it was also reported here, failed to access. So we have our secure policy in place. We have our config file also changed. So we need to rebuild an image in such a way that this mkqnx will take this file also into account. So we will add another option to the build, like option like this. So secpol open and -- policy secpol txt. Okay, let's kill this guy. Okay, let's take a look if those secure policies are in place. We can use the secpol tool to check what are the contents of the secpol bin. Grep test. We have this test app secure policy there, so it was compiled into a binary, so we should be fine. Let's check if our data var secpol configuration was not changed by regenerating the image. Yes, it was, so we need to change it once more. Okay, let's take a look. Stop restricted. Okay, so I also restarted the QNX, so the changes in the config file were applied to secure policies, and I will be deploying once more the applications. Now I deployed them. Let's try to start our test application. The proper secure policy. Okay, we see fault manager could not be open. This is because right now, let's take a look why this is the case. So cat def secpol generate errors, and we see that our test app should have a channel connect to QConti. This is why QConti. This is because our folder manager was deployed with the qcon user. Yeah, this is what we checked previously. We can take a look once more here with this. Yeah. So right now it's running with this type, and our secure policy is saying that we can only connect to the folder manager underscore t. So let's just slay this instance. Okay, and let's start once more with the correct secure policy this time. Now we were able to do it. Vault lock. So this is the basics of the secure policies in the QNX. There is a lot more that can be done with this, but those basics, I think you will use it quite often with the QNX.